Okay, so today we're going to engage in what's likely to be considered a complete waste of my time. But I have this extreme weakness, which is that quantum mechanics really frustrates me. I think in large part because I don't understand it, but also because it feels like it's way more complicated than it should be. And the the experiment that most confounds me is the what's called here in this video the quantum Venn diagram paradox, but what's normally known as the three polarizer paradox. And you can see a little version of it here where it says, there's this like moment where there's these three polarizers, light polarizers, and for whatever reason, even though these are all filters, by putting an extra filter in there, you actually get brighter stuff. So like these two, they're orthogonal to one another, and nothing comes through. But this one, because there's this third one in here, even though nothing came through here, by putting this extra one in, you see more. And this is confounding because it's one of those experiments that you can actually just look at and play with. So you can buy polarizers and play with them, and that means that kind of all of the strange things with Alice and Bob that normally happen when you talk about this sort of stuff, they don't show up like they do here. And so this video talks about it as if it is an illustration of Bell's theorem, which I'm not sure it is. But what we're going to try and do is we're just going to take a look at. I'm going to rerun this. We're going to take a look at some code that I wrote here to about the predictions of quantum mechanics, and then like what you would actually observe if you were doing classical, if you just had classical information, and then what you actually observe and what's required in order to get that thing that you actually observe. This is a hint, the fact that this information has to go in there. And so this paper is called On the Einstein Podolsky-Rosen Paradox, and it's by John Bell. And if you had to summarize the paper, then you would say that what he was proving is that you can't have these two properties that seem like really obvious about the universe. It's called locality and realism. But basically that all of the information that's necessary for figuring something out about the state of a quantum particle, that all comes from the area of that particle. So like if I toss you a basketball, everything you need to know about that basketball is right there with the basketball. It doesn't require you to travel anywhere else. It doesn't require you to, ask me any questions. You can just observe the basketball. So that is locality. And realism is that you have, the properties that are associated with that basketball are real ones. They're not in some like quantum, weird state where there's many, many different properties at the same time. You can just look at it and you can say, oh, look what it is. So that's what this paper purports to argue. I'm not going to pretend like I really understand what's going on here. In fact, I had a lot of trouble converting it into code, as you see over here. But I think that this code is easier to understand. So we'll start there. So this is what, if we go down here, then this is what Bell's point is he says, look, if you're just looking at the correlations that you normally would be able to generate by using the information that you have on hand about a photon and the angle that you're measuring this photon, then this is the plot that you should be able to produce. And yet he says, this is the plot that we actually see, the lighter blue one. And somehow we have to explain that. And this is why he says you can't have locality, you can't have realism. You can't have them both at the same time. So let me draw this for you. Typically and by the end of this, I want to offer you a different explanation of what's actually going on. So, and it's not going to be a complete explanation, but I bet it'll be interesting at the very least. So typically, the way that this story is told is that there's some light source. That's what this is going to be. And then it goes into what's called a nonlinear prism. So let me draw that here. Here's our nonlinear prism. And that nonlinear prism, through mechanisms I do not understand, splits up that light, that incoming light, into two separate but related particles. So let's actually just start with this. So either those particles are going to be those waves are going to be vertically polarized, or they're going to be horizontally polarized, or maybe vice versa. So maybe the vertical is going to be over here and the horizontal is going to be over here. You don't know which one of these states is going to be in. It's just going to be in one of them. And then it's possible to perform a measurement on these. What's going on when you perform a measurement is that you have these long polymer chains, which are exactly the things that you see in that video. And so in that video, those long polymer chains are here in this lens. Polymer meaning just plastic, right? These are plastic lenses. And what's happening is that you have this incoming light. Let's draw our light. And that light has some polarization. So let's draw some polarized light. Let's also draw the magnetic part. We know that electromagnetic radiation is just a wave in the electromagnetic space. So we can draw it like this, just propagating wave in both the electromagnetic, in both the magnetic and the electric fields. I think I can draw these. We won't draw all of them. We'll just draw a couple of them. Let's draw this, put this up here. And I guess for completeness, I'll also draw some horizontal ones here. So boop, 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 boop. Okay, good enough, right? So that's my propagating wave. And when it encounters a polarizer like this, if it's a vertical polarizer, then on the other side, nothing comes out. So that is what happens when it's vertical. If we rotate this, and the reason to think about why this happens is because this electric component is getting absorbed into these polymer chains. They're like oscillating with it. And so they're sucking up the energy. Meanwhile, if we rotate this horizontally, then this passes, no problem, because it's not interacting with those polymers. Okay, so that's the story of what's going on with these polymers. That's how we're performing these experiments here. And so one way we can think about this is visually, is we can just draw a little filter here. This will be our, well, maybe we won't be able to get it back. Here, I'll move this over here. This will be our little polarizer, polarizing filter. And so if it's vertical, it's going to block vertical light. And over here, if it is horizontal, it's going to block horizontal light. And so an interesting thing to think about, and this is what John Bell was thinking about in his article, is what if we have two people? We have Alice and we have Bob. And they receive these photons that are either in this state or this state. We don't know which one. Then what we're not able to measure is we don't know the state of this thing before it receives a measurement. But after it receives a measurement, we can ask both of them, hey, what were your results? And we can get some correlation of the results. So that's the heart of what Bell is saying. And what I'm going to try and show you is that this is going to produce a weird looking plot that seems to have profound implications, but that there's a really simple way that we can explain it away. Okay, so to save us from having to flip those around over and over again, I'm going to move this up, and I'm going to come up with some like visual language for how we can capture this. So can I align you? Line horizontal, and let's align vertical. Great. And so what we're going to say is that, of course, this can either be in a, it can either be vertically polarized or it can be horizontally polarized. And we already know how to do that, right? We use these polarizing filters over here to do that. So there's a polarizing filter. In fact, I think it pops out of this nonlinear crystal already in one of these two states. And if this one over here is in that state, then it must be the fact that this one is in that state. So if it's vertical over here, it's horizontal over here. Or if it's in the dotted case, then if it's horizontal over here, then it's vertical over here. And that's going to give us a nice visual language to refer to these things, because what we're going to be able to do is we're going to say that if let's take Alice and Bob through a whole range of different scenarios and see what the correlation might be between their different states. So obviously, if we start out both vertical and vertical, so Bob is starting out here at 0 degrees angle, then Alice is always going to receive a vertical. I'm sorry, in the case that Alice receives a vertical, that always means that Bob has received a horizontal, right? The dark ones go together. And if Alice has received a vertical, then Alice is not going to measure that this is, she's not going to measure any light out the other side. So we're going to put an X there. And meanwhile, if Bob therefore has a horizontal, because this is the same case, Bob is actually going to measure he's going to measure light. So he's going to say, yes, I saw light. Meanwhile, if Alice receives a horizontal, well, that's going to get through, right? Because this is just blocking vertical light. So that gets through, no problem. But Bob's does not get through because now it's vertical. And so what this tells you, if I realign these, what this tells you is that there is a negative 100% correlation. Whenever this, whenever Alice says true, Bob says false, right? Because that's these two go together. And whenever Alice says false, Bob is going to say true. I think even this is a little bit clearer if we flip these. So let's just do that. Okay. I think this is clear, right? Happy? Me too. Okay, so now we know what happens in this one case where Bob and Alice have their polarizers both vertical. But of course, they could have their polarizers in many, many, many more kinds of states. So let's see if we can do that. Let's move this all the way up here. And we're going to copy this up 1, 2, 3, 4 times. And we know that most of these are actually fine. So Alice is not changing, right? And so if she gets vertical, then it's blocked. If she gets vertical, it's blocked. Nothing is changing here. So this is all fine over here. We don't have to change it. On this side, though, we do have to change things. We have to say that, for example, up here, we want Bob to switch over to a 90-degree angle. So that's going to look something like this. And let's also have Bob switch to a 80-degree angle. So that's probably going to look like this. Let's have him switch to a 45-degree angle. And let's try a 10-degree angle. That's going to look like, sorry. This should be like that. And this should be like this. Okay. So 0, 10, 45, 80, 90. Just rotating through the spectrum. And we're going to arrange right. So now let's figure out, what do we expect to see up here? Well, this is also a really easy case, because if Bob is at 90 degrees to Alice, in this case, then if Alice is blocked here, when Bob is horizontal and Bob is horizontal, well, Bob is blocked over here. And if Alice is horizontal, well, then she gets through. If Bob is vertical, well, then he gets through. So we put this over here. So this would then be 100% correlation. They're perfectly correlated. And if we go back and we look at what we see in here, that's exactly what we expect, but we expect it in all cases. We expect it both in the classical correlation and in the quantum prediction. So far we haven't, so here's 90 degrees right here in the middle. And you can see that, both of them are at 100%. And then here's 0 degrees, and you can see that both of them are at negative 100%, or negative 1. So the interesting ones must be somewhere in between. Well, it turns out that this middle one is also quite simple, except instead of using a check mark, we have to use a percentage likelihood that is going to be in this state. I'll use a smaller. So what we should say here is that 50% of the time it's going to be vertical, and 50% of the time it's going to be horizontal. So this begins to touch on some of the surprising parts of quantum mechanics, as it seems like it requires this sort of intrinsic probability, as though you don't know what state it's going to be in. And the reason that we put that there is because we expect this to be 0% when it's at 45 degrees. We actually expect that both for see here, correlation at 45 degrees, it's going to be 0%. I think I even have a better, let's go to 45 degrees, and it's hovering right around 0%. If I had more precision, I could show you exactly when x is 45, y is 0. And if we go up here, well, now we need to, if we want to figure this out, now we need to ask the, this is Bell's statement. He says that, this is the way to predict what the correlation is going to be. So at 80, we want to expect what does that say? 93.96. At 10, this is going to be a negative 93.96. And that means that we also need to somehow figure out how to fill in the rest of those values. But I'm going to spare you those details, because I don't think that they actually matter that much. And the reason that I think that they don't matter that much, I'm going to give you 2 reasons for it. The first is that what Bell is trying to say with his theorem, in fact, he says it right here at the bottom. Of course, the situation is different if the quantum mechanical predictions are of limited validity. Conceivably, they might apply only to experiments in which the settings of the instruments are made sufficiently in advance to allow them to reach some mutual rapport by exchange of signals with velocity less than or equal to that of light. So what he's talking about here is that it seems to imply that there is the ability to propagate information instantaneously, so that a theory could not be Lorentz invariant. And this is sort of a euphemism for we are cheating by sending things faster than the speed of light. And that would be really strange, because it would violate quantum mechanics. Now, every physicist alive today would say that no, it is not possible to propagate information faster than the speed of light. Even people who are working on so-called quantum teleportation will agree that what they're doing is they're transmitting states, and in order to transmit a state, they have to destroy a local state. So it's like they're teleporting information, but they're not teleporting it faster than the speed of light. And so Bell's theorem seems to like potentially imply that you can do this faster than the speed of light. Physicists today agree, no, you can't do that. What I want to show you is kind of an intuitive reason for why that's not the case. So what Bell was getting confused by is Bell was taking this function, and you can actually see it here right in the code. Here's the measurement function that you have to write if you want to make this plot appear, where these green dots land on the predicted dots. And the function that you have to write is very strange. It takes in as input a photon, so the angle of the photon, the angle of measurement, so Bob's angle of measurement over here, 90 degrees, 80 degrees, 45 degrees, and then the entangled partner's angle. So if we're measuring for Bob, Bob needs to know Alice's angle, in this case 0. If we're measuring for Alice, Alice needs to know Bob's angle, whatever this is. And this is really uncomfortable because, of course, at the end here, you have to get out this curve, and this curve is verified by all kinds of experiments. I'm about to tell you where this comes from and why it's not even vaguely surprising that you need to know this information. But before we do, I want to take you a little bit down the track of what can happen if you get confused by this. So let's do stack physics stack exchange. And I'm going to show you a recreation of what's called the delayed choice quantum eraser experiment. So this is a recreation of the diagram that was in that this article called the delayed choice quantum eraser experiment that got a lot of people really confused as to what was happening in quantum mechanics. It seemed like maybe what this was allowing was for information from the past to influence the decision of a detector in the future. That was what it seemed like was happening. And if you'd like, you can visit this question and check out this commentary, and even I think there's a video in here as well that, as it says here, devolves into magic by the end. And so, this experiment seems to have these profound and physics-defying consequences, and yet all of the answer to the supposedly confusing questions is found not in this diagram, but in this little blue box onto the side, the coincidence counter. Because essentially, what the mistake that Bell is making is he's saying, okay, in order for us to get this output diagram of the correlations, we first, it seems that we're required to have the angle of the partner. And he would say, this is the only thing that we can measure. That, we can measure their, when they say true and false on some statistical level, and then out the other side, we expect to see this plot. And he says, that seems really mysterious. It's what makes it not so mysterious, the reason that you should find this unsurprising is because in order to compute the correlation, you have to have the information about these two. So the correlation itself is the place where that mutual information is showing up. The reason that the coincidence counter over here works in order to seemingly produce impossible outcomes is merely that when you are counting those coincidences of both true or both false, that information is all shared in one place. So it ends up being a totally, in fact, there's kind of a funny way to say it, which is that what Bell proved rigorously was that in order to compute the correlation between Alice and Bob's states, you need all of the information about Alice and Bob's states. And when you put it that way, it's not that surprising of a result. That said, there's one strange thing that's left over from the experiment, and that is that when you assume classically how you would think these would be correlated, they take on this shape, this like A-frame shape, and then when you perform the experiments, you find that they have these curved shapes. And so what I want to offer as a possibility to explain this, this seems like surplus energy, right? How is it that we're getting more correlations? Like when we have tiny angles here, how is it that we're getting these major differences? And the possibility that I want to play with is that a way to explain why it is that this. So let's just remind ourselves of what the three polarizer paradox says, and then we'll wrap this up. Is that okay? If we have some vertically polarized light, let's go get our vertically polarized light set up. And so, incomes are like bright light source, totally uncorrelated. It doesn't need to be that big. And it can be this color. Okay. Incomes are bright light source, totally uncorrelated, passes through here, which means the only thing that can be left is the vertically polarized light. And then in one experiment, we then pass it through this, and nothing comes out the other end. In another experiment, we rotate this by 45 degrees, and we get a little bit of light that comes out the other side, but not a ton, not as much as we started with to begin with. And then we finally pass it through that final filter, and we still get light coming out the other end. And so that apparent paradox is still there. It's like, wait a second. Here we have effectively one filter. Let's call it two filters. Here we have two filters, and we get no light. We add a filter, and we get more light. How is that possible? It's like having a sieve, and you have rocks going through the sieve. It would be like if you added another sieve in there that would normally filter out more rocks. Suddenly on the other side, you saw more rocks. It's like something about that is strange. But there's potentially a really simple explanation that I think is consistent with our observations in quantum mechanics, which is very simply that, okay, you have some starting amount of energy, and when you pass through this filter, it takes out, some of the energy, and all that it leaves is this vertically polarized component. And then when it passes through this next filter, what it should be doing is it should be rotating a little bit and then also reducing its energy. And then we can pass it through this next filter. And whereas over here, what's happening, we pass it through that filter and then it slams into this thing. And when it does so, it can't manage to rotate kind of fast enough. And so it all gets just absorbed. When it comes in over here, we still have some energy that's horizontal now because we've partially polarized it. And so yes, we lose some energy here, but we also rotate a little bit more. And that to me feels like a perfectly elegant and complete explanation of what's going on. To my understanding, we can already do this. So you can circularly polarize light. I think you can do it with something kind of like strange, like milk or something like that. Just Google like circularly polarized light with, probably it will give me a hint. Steve Mold, I know, has a video on this. Sugar can circularly polarize light. And so, that circular polarization seems to be an indication that it's possible to to rotate your light more and more. Okay, so that's my sense, is that there's a possibility that what's happening is that the reason that you require information about Alice and Bob's state in order to figure out the correlation is because in order to figure out the correlation, you require information about Alice and Bob's state. And it's actually not as profound as Bell thought it was. And that this additional bit of energy that you see here above and below the curve, where you're getting kind of more correlations than you would normally think as you approach 90, or as you approach 0, that those come about as a result of the fact that it's possible to twist light by using polarizers. And so can be seen as unfairly favoring one of the sides. So in this case, if this came in vertically and this came in horizontally, then it would increase the correlation above the expected 90%, like your naive 90%, because not only is it randomly, it's not merely randomly triggering, but it's also has some probability of being able to overcome this fact that it's out of phase, and it's twisting it just a little bit, and instead of merely destructively deciding either pass or don't pass. So this would be my best guess at how you can resolve this kind of, essentially what this comes down to is an extra 4%, 3.96%. Where is that extra 3.96% coming from? And this to me feels like a way more understandable explanation than strange things about non-locality and don't even get me started on quantum slit experiments and whatnot. So I hope you enjoy my cranking about, and I'm curious to know if anyone knows anything more about this, that they can say, nope, that doesn't work, and here's how we know that polarizing filters don't twist light, or here's how we know that polarizing filters twisting light isn't sufficient to account for the additional correlation. And if that's the case, then I would love to hear from you. Thanks for watching. Bye.